start the morning session, being 10 a.m., I believe. So it's a pleasure to introduce Professor Anatoly Libgober from University of Illinois at Chicago. And Professor Libgober will talk about many of the titles of the conference. So we're very happy to have you here. So he'll talk about equivariant genera, spectrum of isolated singularities, and hybrid models. Professor Libgober, you're free to speak. If you need to tell us anything or need to tell me anything, simply tell me and I'll join and take the microphone and I'll live.
Oh, okay. No, everything fine. I'm good to go. Yeah. Okay.
Then good morning and please start.
Okay, great. Well, thank you very much. Thank you. Привет, Людмила, привет. Okay. Yeah. Thank you very much for this great introduction. Well, thank you very much for inviting me. And I'm sorry I couldn't make it in person. Well, hopefully next time. Okay, well, let me. Oh no. Oh, okay, good. Okay, well, let me start telling where is motivation for this talk comes from. So the main motivation actually to understand what Witten called hybrid models. So and geometric backgrounds, which I underlined, and so how to assign invariants to these backgrounds. So the first case of this of these hybrid models that so-called LGCY correspondence. And well, so right away I should just make this disclaimer. So this LGCY correspondence, it goes to the very early days of sort of string theory and mirror symmetry, basically to early 90s. So at the time, so LG, so that's what was preceding Kontsevich, was the sort of generalization of this concept of Landau-Ginzburg model when this is a quasi-projective variety, some function, and so on. So in that time, so LG model that it meant well CN and the function which is weighted homogeneous, and so the LGCY correspondence, that was well people like Waffa and Berglund were discussing. That's so there's some. Isolated singularities, relation between isolated singularities and Calabi-Yau hypersurfaces in weighted projective space. And since then, so this correspondence was intensely studied. And also another general comment. So like just in Kontsevich, it's sort of mirror symmetry of for Fano varieties. So the Landau-Ginzburg is a mirror of the mirror of the manifold. So here actually Calabi-Yau has its Landau-Ginzburg model, and the mirror of Calabi-Yau also has mirror Landau-Ginzburg model. And so while mirror correspondence sort of exchange A and B models, so that the LGCY correspondence actually preserve them. So there is one particular, there is a LGCY correspondence for A models and for B models, and and all those was studied. And so and that was mentioned. Well, Kyoda, Iritani, Rohan, and Prius, Shoemaker, and Kyakanfen and Kim started correspondence between Gromov-Witten invariants and this FJRW theory. And Kyoda, Nagel, and Clutter, they study B models, and then derived relation between derived category and matrix factorizations, and GIT quotient also was studied by Orlov, Katsarkov, and Halpern Leisner. So, and there is very long list actually of activity in this area, and so that And I did miss a lot of names, especially those who work recently on that, more recently on that. So now, Witten in his 1993 famous paper, Phases of N=2 Theories, generalize this. So instead of relation between weighted homogeneous singularities and Calabi-Yau hypersurfaces in weighted projective spaces, so he replaced this hypersurface by complete intersection product projective spaces, Grassmannians, and so on. And moreover, each background has not just one partner, like Landau-Ginzburg partner. Actually, it has many. It can have many models. So the motivation here is somehow to understand invariance of this model, which Witten also describes on physical language, and so it's not entirely clear what sort of mathematical generality it may or may not work. So this question was started in my paper just in 2015 and 2018, and so this talk, it's about report on some progress for further understanding of this correspondence. Okay, so this talk more precisely mathematical definition of hybrid model and some of the invariants like chi-sub Y genus and elliptic genus. And then, so the main thing, so I also explained this equivariant interpretation of spectrum of weighted homogeneous and Newton generic singularities. Yeah, but by the way, I want to also, please feel free, interrupt me and just ask any questions at any moment of the talk, and don't wait until until the end or anything else. Okay, so now that was sort of just give just general idea where I'm heading to, and so what's the problems I have, issues I have in mind. So now let me explain just that just on this toy example. What is this LGCY correspondence just for Euler characteristic? So let's look at the Euler characteristic of a hypersurface of degree D in projective space dimension n-1. So it's this is formula. So in your undergraduate course in algebraic curve, you you use this formula for n=3, the genus of plane curve. So now, but what one wants to do, so one wants to somehow relate this to the Milnor number of this singularity, x1 to the d and so on plus xn to the d, and somehow this what Waffa tell it should involve arbifieldization process. Okay, so now let me remind what we already heard in many talks, in particular of Ernesto talks. What's this orbifold Euler characteristic? So if we have finite group acting via bioholomorphic automorphism of complex manifold, then the orbifold Euler characteristic is sum over conjugacy classes of fixed points of gamma quotient by a centralizer. Okay, now this can be also just rewritten very compelling ways, so just like similar to the Lefschetz formula for Euler characteristic quotient, just the sum of the pairs of commuting elements. Okay, so one can view this as sort of one can use naive extension this for pairs for pairs of topological space. Yeah. Okay, so now it's also satisfies. So that this is non-trivial fact. So that's also was mentioned in Enrique talk before. So that McKay correspondence. If we have a crepant resolution of this global quotient orbifold. So then Euler, this orbifold Euler characteristic actually Euler characteristic of coincide with Euler characteristic of Crepant resolution. So and so he was mentioning sort of just a relation to classical McKay correspondence, where a relation between components of resolution of two-dimensional singularities with the conjugacy classes. Okay, so now now, how to obtain through orbifoldization and from Milnor numbers this Euler characteristic of Calabi-Yau hypersurface? Well, so now let's consider the singularity, homogeneous singularities, and consider action, which is associated with the group of unity of degree D. So this is action on Cn, I'm sorry, on CD. And notice, by the way, that here this number of variables is the same as degree. So in other words, I do restrict here to the case of to the Calabi-Yau case. So and now what we do orbifoldization for Euler characteristic of the complement CD minus Milnor fiber. Let's just apply this familiar formula from previous slide to this particular topological space. So now if you have a pair of commuting elements, but both are identities, so then the fixed point set is this whole complement. And the Euler characteristic is 1 minus d to the d, which is up to sign the Milnor fiber of these singularities. And now if at least one of the elements is non-trivial, then fixed point, there's only one fixed point, so and there are, which contributes 1. And so you sum up of all this, all non-trivial pairs of non-trivial elements, so you get this d squared minus 1. So, what I'm aiming into, so just extend to this to more sort of sophisticated invariants than just Euler characteristic. So in particular, so the issue is how to orbifoldize spectrum of this isolated singularities. This is isolated singularity. Okay. Well, are there any questions? All right. Okay. Well, let me remind the definition of the spectrum. So that so if you have a germ of holomorphic functions, so it's a much more general context than just weighted homogeneous singularities. And that goes back to, of course, there's this definition due to Steenbrink. So who constructed a limit mixed structure on the Milnor fiber. And so and because monodromy acts on Milnor fiber, and so you can decompose in semi-simple part, and semi-simple part preserve mixed Hodge structure. So then you can look at PQ spaces, and look the eigenspaces of semi-simple part of monodromy, acting on this space HPQ. So this is graded of homology of Milnor fiber. So that gives you an number of rational numbers. So this total number or number with multiplicity is the same as the Milnor number. And so it's basically, which means you take logarithm of eigenvalues and assign integer part to this logarithm, depending on the Hodge filtration of the group in which this eigenvalue appears. Okay, one can consider Poincare series, and that's what's the spectrum of singularity. So multiplicities of this spectral numbers, and well, just usual Poincare series for this sequence. So now this is Steenbrink calculated spectrum and weighted homogeneous case. And so here's the formula. So by the way, here's the weighted homogeneous polynomial of weight W1, Wn. So it contains this monomials which exponents satisfy this relation, which is written there. Sum AI Wi is 1. So okay, so we have this spectrum. Now the problem is how to relate this to the Hodge polynomial of Calabi-Yau hypersurface in Pn minus 1. So in other words, what is the arbifaldization procedure? Well, so now the idea to reinterpret this Steenbrink spectrum in a way, so in terms of equivariant invariants, okay, in terms of certain equivariant invariants. So, and that's what I want to explain now. So basically, this procedure involved the arbifaldization of Hirzebruch chi-sub-y genus. So just this procedure is the same for in fact well much more general genera. So just let me recall. So by genus I mean just homomorphism from the unitary coordinates into ring R. So and ring R could be integer, could be ring of polynomials, and also it will be, in the case of elliptic genus later, it will be ring of Jacobi forms. So, and so genera one can construct as the sort of value of holomorphic Euler characteristic of various bundles attached to the manifold. And so here that there is this formula for chi sub y. So it's a Poincare series, which is Hirzebruch chi sub y genus, which is a Poincare series for the holomorphic Euler characteristic of P of exterior powers of cotangent bundle. All right. So now, what's very important about the genera, so they can be, they all can be calculated as combination of Chern numbers, but only in the in compact case. So that's typically this identification goes through Riemann-Roch theorem, and so the expression of particular genus depend on a series Q of x, which is appearing in this formula, and if you factor some of the Chern classes in the form as in the slide, so xi is Chern roots. So then, and if you consider this phi of x is a symmetric function of xi's. So in elementary symmetric functions of xi's, they are Chern numbers. So you obtain expression for phi of x in terms of Kerr numbers. And so now specific Q series, they are just also just written here. And so later, that's for earlier characteristic and for the series Q for tot genus and series for chi sub y genus. And later it will appear this power series Q for elliptic genus. Okay. So now what I want to make sort of interpret this Steenbrink spectrum of weighted homogeneous singularities and more general singularities in terms of equivariant chi sub y genus. Okay, so let me briefly remind about equivariant genus. So if you have like a sheaf F, so so you can consider character value earlier characteristic. So where's just so you take cohomology of the sheaf and on which here also torus acting on manifold X and the sheaf F. So then the cohomology torus acts on these vector spaces H I X of F, and so you can take character of this representation. This way you get character value. The a function which you attach to sheaf F. So in particular, so this character value dimension it becomes not integer, but rather a series in the characters or in the characters of this torus T. So that's what's written on just on the lower part of this slide. And so the character value earlier characteristic can be calculated using equivariant Riemann-Roch theorem. So that involves definition use of the equivariant Chern character, which naturally take values in equivariant cohomology. And in fact, one need to do a little more. One need to do completion and obtain just a ring of the power series in the characters of the torus. So so there is refining this invariance, and so what sort of makes equivariant cohomology much easier to use than in some sense than ordinary, it's localization. But by the way, so here I should say that so here all this discussion goes in the algebra geometric sort of category. So of course, as Enrique was mentioning in his talk, so that all this equivariant theory goes back and localization goes back to T and Bott. So here this in algebraic geometry, so this was worked out by Yedidin and people like Tatara and others. So so now what is important here? So just like this equivariant Euler characteristic chi t x of f, so it just can be calculated only from the data from the fixed point sets. And yeah, let's see, is that okay, so it's essential. So this localization formula is written here. So and a contribution of each component of this fixed point set, it's just restrictions of the f on this fixed point set, and corrected by the Chern class of the normal bundle. Okay. So in a moment, I'll be doing just very concrete calculation of that, so to illustrate all that. Yeah. So now, in particular, so what we get, the local contribution. So what gives us this invariant, this localization gives an invariant is the local contribution of component of fixed point set. So for chi sub y genus, which I did write here is explicitly. Okay. So here xi, so there's a Chern roots of tangent bundle. So equivariant Chern roots of tangent bundle restricted to the component f, and so as you see here, it's corrected by the top Chern class of the normal bundle. Now, okay, so now what's localization theorem gives sort of it doesn't give meaning to geometric meaning to any individual local contribution, but rather the sum gives you this character valued Euler characteristic of the sheaf on a compact manifold. So the idea here is just to look just look local contribution individually, and try to use just this local contribution. So advantage this local contributions can be defined on non-compact manifolds. Well, but still assuming that fixed point set has fixed point set is compact. But the price for that, there is no clear geometric meaning of this local contribution. So nevertheless, so that it's one can give sort of intrinsic sort of definition of this more intrinsic viewpoint on this local contribution. So and one can view this as a motivic realization of certain certain K theory of the manifold. Well, and so here one describe the class of the quasi-projective manifold. One should just look. It's which has for which fixed point set are projective and have positive dimensional normal bundle. So one organizing K theory, not all manifolds, just like was done, sort of just classically, but just so one create this such equivariant version, this K theory. And so the local contribution defines is a realization, like similar to the Hodge realization of the in the K theory of the variety. So local contribution defines homomorphism and the localized ring of the character. Okay, so that gives sort of intrinsic more intrinsic description. So there is something beyond just this local contributions which are given by this specific formula. Okay, and finally, I just noticed that it both Riemann rock and localization can be defined in non-projective case, non-projective and singular case. So, but it lives sort of in the it lives in the case of toric manifolds. It was done very explicitly by Brion and Verne sometimes back, and so so they have sort of this what's written here. So just F is a sheaf on the a fine toric variety which corresponds to the cone, and so that's the function which Riemann-Roch theorem calculates, and one can write this in the Riemann-Roch form, just like as written here. So basically, in what follows, we will need to use local Riemann-Roch on singular varieties or orbifolds, in fact, not very singular. Okay, so now let me just now here's the theorem about the relation between spectrum and the equivariant chi-sub Y genus. So suppose F is weighted homogeneous polynomial, and then with each weighted homogeneous polynomial associated C star action, for which this polynomial is eigenvector, and so this is C star action on Cn. So, and then the spectrum, which is this left-hand side, can be identified with the local contribution into chi-sub Y genus. Okay, so that's but in this formula, which is written, so left-hand side depends on one parameter T, while right-hand side depends on the character T, and also depends on Y. So in fact, to get equality, if one get equality, if one takes only Y equal T. So identify this variable, which is a formal variable in chi-sub Y genus. One actually identified character, and so in other words, this variable should get get this geometric meaning. Okay, well, let's look at the in the case of weighted homogeneous. So one can actually make explicit calculation of both sides, and just to check that one get the same formulas. But in the moment, I'll present just a more intrinsic proof of this, which in particular will explain why one make this normalization Y equal T. So Now, if we take this polynomial, which we discussed already before, like sum of the power, so sum of the nth power, x1 to the n and so on plus xn to the n. So the corresponding, there is corresponding C star action, and there is the subgroup which acts trivially. So subgroup roots of unity. So what one need to do, one take equivariant genus of Cn, obtained via localization. But calculate this not on this on Cn, but on the quotient. So on the space where C star action on is effective. So now the local contribution just can be calculated by this formula which we saw in this localization slide. So so we have this product. So you see the familiar formula for chi sub y genus, generating series chi sub y genus, and the u over n. This is u is equivariant equivariant Chern root for of the normal bundle to the fixed point to the origin. And so here we put this u over n because we actually calculate relative to not the C subgroup C star which acts on Cn, but rather so we interested in character C star quotient by mu n. So therefore we use the as character u over n. And for this, you have this correcting factor, correcting Chern class of the normal bundle. And so that's, you calculate local contribution. And indeed, if you put y equal t, so you get this expression, which is a formula we saw before, which is Steenbrink formula for the spectrum of weighted homogeneous singularity. Okay, so one can check this directly. So, but here this intrinsic explanation of for this relation. So if it goes, so the key thing, it's a use of Newton filtration. I associate actually to any to polynomial generic for its Newton polyhedron, and this and the C star action relation between Newton filtration and C star action, which exists in weighted homogeneous case. So let me remind, so this definition of Newton filtration, which is going back to Kushnirenko, and then of course just widely used since. So you start with the polynomial and consider a Newton polyhedron, which is convex wholes of monomials. So in other words, some polyhedron in a space of characters. So if you view this Cn as toric varieties, so that so this is some convex polyhedron. So in a group in a space of characters. Okay, notice that because here, since we're dealing with the function with local situation, this is Newton polyhedrons non-compact. Okay, and then you find homogeneous function which takes value 1 on this on Newton polyhedron, and so Newton filtration monomial Newton filtration of monomial M is just value of this function. So now the relation between the main point, so that the spectrum actually can of isolated singularities generic for its Newton polyhedron can be expressed in terms of Newton filtration. So now so this was conjecture by Steenbrink and proved about 10 years later by Saita in '88. Now he considers sort of cohomology Milnor fiber is identified with this space and form quotient by this subspace, and now this now one consider filtration induced. So see this omega n is subsheaf. If you look at Stokes subspace of the of log differentials, and log differentials have this Newton filtration, which is given by Newton filtration on this local ring, as was sort of described just before. And so then one take a restriction of this Newton filtration on log differential on ordinary differentials. And so the Poincaré, what Saito shows, that the Poincaré series for this induced filtration coincide with the spectrum. Okay, so once one knows this, so one if F is weighted homogeneous, so then one has a C star action on this log complex, and so then one can ask what is sort of a Poincaré series for the or this character value for this C star action on this space. And so what one can right, so well, this quotient space, so it has of course resolution by the well, it has the RAM type resolution, so with differential just taking exterior product with df, and so the character of this this algebra so can be calculated in terms of the RAM resolution. So explicitly one get this formula for weighted homogeneous singularities. So this is not a spectrum. It's something different. But then one, according to Saito, one has to pass to subspace. To this, in other words, but exterior algebra subcomplex of log differentials, and so now the point that the this differential df, so it has Newton degree 1, and so that sort of accounted for this fixing y equal t as well. So yeah. So from so that gives sort of explanation. So just in terms of Newton explanation why one does this fixing. Well, are there any questions about it?
Very nice.
Well, well, let me. Okay, thank you. Yeah. Okay. Well, so now this is also as allows for so this approach also allows for equivariant interpretation of spectrum of singularities which are weighted for its Newton polyhedron. So basically, one consider this Newton polyhedron, and for each phase, to each phase corresponds toric variety. So the cone on each face. So for each face you have cone, and this cone gives you toric variety, and you consider C star action, and it turns out this spectrum spectrum of of a function generic for its Newton polyhedron will be just a certain combination of this equivariant spectra. So that suggests so that it could be some kind of LGCY correspondence for not just for weighted homogeneous, but for some Newton generic polynomial. So that's sort of a work in progress still. Okay, now, well, I guess I have to speed up. So now let's, since time is short, let me go back to this Witten description of the LGCY correspondence, and to show how this this equivariant interpretation of spectrum allows to get this identification of our bifoldized spectrum of weighted homogeneous singularity and the and some Calabi-Yau hypersurface. So just Witten considers C star action on not just Cn, and he adds one extra variable on Cn plus one, extra variable P. And he considers GIT quotient for this action. So it's there are two GIT quotients now, and one is Cn quotient by the mu n, and another is total space of the normal a total space of a bundle of minus n on Pn minus 1. So, so in particular, one can see very easily sort of birational equivalence here, or even K equivalence. So just this second space is just desingularization of the first one. So now, but once you take GIT quotient, there's no C star action left. Well, then so that sort of some indication that this assignment invariance just may not work so well for arbitrary GIT quotient. But one needs some extra structure, and I'll describe this in a moment. But in this example, actually, this extra structure, it's easy to see. So you have additional C star action, just dilations on the last n variables. So now what I propose to calculate just the chi sub y genus, or local contribution of chi sub y genus for this for this dilation on each of these two GIT quotient. Okay, so and what we will see that well, the Cn quotient by mu n, it's orbifold. So what one need to, so in particular, one can take not just chi sub y contribution of on Cn cross a quotient by mu n, but actually to take orbifold version, like orbifold, because this is orbifold, just take into account this group mu n, and then we show that this this after orbifold, taking orbifold version of this local contribution, one can get this chi-sub y genus of well, some chi-sub y genus type invariant of on this normal bundle, which it turns out coincide with the chi-sub y genus of hypersurface. Well, my time is only almost up, so maybe I just go to so here I wanted maybe I should say about just definition. In which context so I can define this invariance of the faces. So one takes not general GIT quotient, like G acting on arbitrary group, space, quasi-projective G manifold X, but actually one look at the action of the total space of equivariant bundle L. And then one take a GIT quotient of the total space of this bundle. So, so the advantage that you get this dilation of this bundle L. And so what you do, you calculate the local contribution of this dilation, which is the C star action, which is a dilation acting on this bundle L. Let's see. So here just so here how it works in this example of the CY of this GIT quotient related to CY LG correspondence is described by Witten. Well, and I guess I started to show that this calculation for elliptic genus. Maybe I'll just finish with the example, which shows sort of just sort of in the end of the day, so that this for LGCY corresponds for chi-sub y genus. It reduces to identity. So, well, chi-sub y genus of Calabi-Yau hypersurface certain polynomial and y, and a spectrum. It's also certain polynomial, well, in t or y. So here, of course, we identify y and t, and so they. If one put together all this orbifold formula for chi-sub y genus for orbifolds, so one can get a formula which is just on the first display. So here you see if k equals 0, you see this formula which for spectrum, which appears already several times. So this is so in this in this sum. So this only a term corresponding k equals 0 is the Steenbrink spectrum, and this the full sum, that's sort of result of creating orbifold version of the local contribution of this of the local contribution. And so once one transformed it, like for n equal 4, for small n, it's one can just make all these calculations by end, and so you get chi-sub y genus of K3 surface. So yeah, well, maybe I'll stop here. Okay, so yeah, I'll stop here. Thank you.